I'm rolling a ball across the table and you're trying to predict where it's going to be, you know that within a certain time interval, it should be within a certain position. That's a crude estimate here. So this uncertainty in time, or this range in time, would just be m times the change in position over the momentum. Nothing particularly of great wow factor. Let's bring in the Heisenberg, not wrong guy, the Rayleigh wavelength, which is h over px. And so the momentum of the particle should just be h over the wavelength. That's the direction I want to go in. Actually, I want to keep it this one. I don't need that part. I know that the speed of the wave is equal to the frequency times the wavelength. And so the frequency is equal to speed divided by the wavelength, which is, you get that right there. Dx over h. To do that slightly differently. The momentum divided by the mass over the wavelength, which is h over 2x. And so we have a frequency here of tx squared over hm. If I want to figure out what, I've got some change in the frequency, it's not a definite value, so basically I want to take a derivative. So what would df be equal to, given that f is equal to this? If I said df dp?
2px over hm.
And then macroscoping it. So this uncertainty in the frequency, which is equal to 2 times the momentum divided by mh or hm times this uncertainty in momentum. So if I multiply these two things together, I get this change in time, this uncertainty in time times the uncertainty in the frequency is equal to m delta x px over try that again. Over there, mass times the change in x over px times 2px over mh delta tx. If we think about frequency and period or reciprocals of one another, these, again, this is just a quick and dirty derivation here. Again, 1 is equal to, well, m cancels out, px cancels out. I'm just going to take h over to the other side. So again, h over 2 is equal to delta x, delta tx. Now, officially, this uncertainty in the position and the uncertainty in the momentum of an object is going to be greater than h bar over 2, but to get from here to here requires a whole lot more depth that we don't have background for. But we have a pseudo derivation, at least to get you in the general ballpark. And this is one of the three forms of Heisenberg's uncertainty principle. And it's claiming that the more detail I know about the position, the less detail I know about how fast it's going, or momentum in general. Or the more information I have about this, the less information I have about this. Thus, the physics joke. Heisenberg's driving down the street, gets pulled over by the police. He rolls down the window, the policeman says, "Do you know how fast you were going?" And he goes, "No, but I know where I am." Let's get rid of that. All right, Schroedinger. Yeah, we got time. Because I have to get to the second part of that joke. If we were dealing with lenses, I have a focus joke. I have a logarithm joke too. You will never get to hear them. All right, so we have this idea of uncertainty that in information. Schroedinger was taking it from a different tact. And there's a textbook that it's at home right now, thanks to the pandemic, but where someone talks about the way quantum physics was developed of people just taking absurd guesses that happen to be right. This is one of those absurd guesses. That's not the absurd guess yet. I am going to make one change. This is the way I've been writing it, U for potential energy. At this point, at some point along the line, it goes from being U to V. So we're going to go within keeping of sort of the tradition for this development. V, and this is potential energy, not potential. K, kinetic energy, and let's go for it. What's the formula for kinetic energy?
1/mc squared.
Well, I heard it, so I appreciate that. I heard multiple voices. Enthusiasm, which we'll work on next. And this is just mv squared over 2, obviously, which is m squared v squared over 2m, which is p squared over 2m. So oftentimes kinetic energy is written in terms of momentum. I know the de Broglie wavelength is h over p. And so p is equal to h over lambda. Okay, no, we're still good on that. If we think about waves, we talked about this when we were dealing with electromagnetic wave, that the generic formula was some amplitude times the cosine of kx minus omega t. What was this k?
Position offset, like depending on where you started.
Oh, no, that would be if I have plus phi over here. Oh, I guess,
The
no, that would not be position offset.
wave number?
That's it, wave number. And the wavelength is just 2 pi divided by the wave number. So this is a lowercase k as opposed to the uppercase k over there. So therefore, P is equal to h over 2 pi over this lowercase k. Which is k h over 2 pi. If I plug that into here, I get k squared h squared over 4 pi squared. Oh, actually, that's just h over 2 pi, so that's just k h bar. So I get k squared h bar squared over 2m. And therefore, k squared is equal to 2m over h bar squared times the kinetic energy. And so if we think back to a wave over here, and let's keep it time independent. There's two formulations of Schrodinger's equation. Typically you go into the time independent one, so this whole term drops out, and then there's the time dependent one. So we'll start with the time independent one. So I have some function, a cosine kx. I'm gonna ignore the plus phi. What would be the derivative with respect to x?
Negative AK sine KX.
And then the second derivative,
Negative AK squared cosine KX.
negative ak squared.
Is that like psi? What is that?
That is a psi.
Okay.
And that is equal to, well, a cosine of kx is just psi. So this is, so I have negative a, wrong one, negative k squared psi. And k squared is equal to that. Negative times psi. Therefore, k times psi is equal to negative h bar over 2m times d squared psi dx squared. And now I know what you're thinking. You're going, wow, that's just incredible. How did no one else think of that? Here's the implication. E times psi is equal to k plus u times psi. I'm going to distribute. E times psi is equal to k psi plus u psi. Sorry, I switched it to d. K psi is equal to negative, there we go, h bar over 2m times the second derivative of psi with respect to position. We now have an equation to describe something that is a wave. So if I give circumstances, if I give boundary conditions, we can now figure out what psi is in order to describe the particle. I'm going to jump through, skip over some massive derivations here. I'm sorry. So for example, if I talk about the infinite square well. So an infinite square well is a square well which basically the potential is infinitely big going up the sides and it's zero in between. So just picture sort of like a well, and I've got basically nothing blocking my particle down here, but there's no way it can escape. And I want you to figure out what is a wave function using this equation right here, which would describe it. Jumping to it, to the solution. The infinite 1D square well, there we go. You ultimately end up with psi equals some amplitude times the sine n pi x over L, where this is 0, this is where x equals 0, and then x equals L. This describes this wave function given the boundary conditions, and the wave function would look something like that. A, as it turns out, is equal to the square root of 2 over L. And so we now have something that can describe a particle in an infinite square wheel. From this, we can also now come up with energies based upon this letter n here. So when n is equal to 1, 2, 3, and so on, we can start getting energy levels. Taking it one step further, let's not get the infinite square wheel there. Let's have a finite square wheel. Let's go ahead and make it finite on both sides. So now the particle can actually physically exist outside of the boundaries here. So just imagine that you've got a square wheel and something inside of it. In theory, in classical mechanics, if it has enough energy, it can make it over. In quantum mechanics, well, we're not really dealing with a particle actually in a box here. We're dealing with something dealing with potential energy, that if I described it, part of that, the wave function would actually exist inside the barrier here. As in, there's a certain probability that the particle would not be within the confines of it, but would actually start going into the edges. Which is all well and good. However, suppose instead my square wheel looks like this. If it can exist inside here, then at some point it actually could exist outside here. That there's a non-zero probability that this particle might exist on the other side of the barrier. Which seems crazy, that if I have something inside a box, in classical mechanics especially, I have something inside a box and suddenly it can appear outside the box. This is known as quantum tunneling. It doesn't have enough energy to make it over the barrier, but it does have enough to make it through the barrier.
Whose equation is this?
Pardon?
Whose equation is this?
This comes from Schrodinger's equation.
Is that where Schrodinger's cats come from?
That's the one.
Okay.
So quantum tunneling is the basics of basically the electron tunneling microscope. You bombard electrons at a barrier, and there's a probability that the thinner the barrier, the greater the probability one of them will make it through. It's not like you're shooting a bullet through it and there's a hole that appears. It's that the particle somehow exists outside the barrier. And the electron will appear outside the barrier. And again, the smaller the barrier, the more probability that the electron's going to make it, that an electron will suddenly appear over here. So leaning against the wall right here, there is a non-zero probability that I will suddenly appear in the bathroom. Except for the fact that you're looking at me. So we get Schrodinger's cat. When you have this equation right here, you're basically setting it up so that if no one's observing it, all possibilities are possible. In Schrodinger's cat, you have a cat inside a box, and there's a timer going off that there's a certain probability radiation is going to be emitted and the cat's going to die. So the question is the cat alive or dead after a certain amount of time? What Schrodinger's and the interpretation of quantum physics says, yes, it is alive and dead until someone observes it. Once someone observes it, it's called collapsing the wave function. You take it from all the possibilities into there's a single possibility. This is why you're preventing me from quantum tunneling into the bathroom. Because you're collapsing my wave function. Now, as soon as you look, the cat will be alive or the cat will be dead. But until then, both the way you would describe it is it's alive and dead at the same time. Just like the particle is in the box and outside the box at the same time until there's some observation which basically puts it one side or the other. in the Davidson-Germer experiment where they shot the electrons at the double slit, and you had the pattern there that looked like a wave. It's when the electron hit the barrier right here, it collapsed into a single point. And so that's why you're not looking at a whole bunch of electrons at once, and similar to that you would do with light. What you're looking at is an electron hits and it scintillates in one spot, and then you just do a whole bunch of them and it starts to show a pattern at some point. But as part of the experiment, they put a detector here just to see which slit it was going through. As soon as they put the detector there, the pattern changed into a whole bunch here and a whole bunch here. It destroyed the wave pattern as soon as that they put the detector there. Remove the detector, it goes back to being a wave until it hits the screen.
That's weird.
So, Heisenberg's in the car, Schrodinger's next to him, and after Heisenberg says, I don't know how fast I was going, but I know where I am, the policeman got a little suspicious and said, open up the trunk. So they popped the trunk, and the policeman said, hey, do you know you have a dead cat in here? And Schrodinger goes, well, we do now. The other half of the joke. Yeah, so this is basically the start of quantum mechanics. A couple other just little bits and pieces coming off of this. There is no infinite square well, but we do have finite square wells. If you think about an atom here, that there's a certain place that the electrons like hanging out near the atom. They're sort of stuck in a well, in a sense. But it's a finite barrier to the next one. And so if you've got a conducting material, then this barrier here between them is small enough for the electrons to be able to easily move back and forth. They transport easily. Semiconductor, you got the square well here, and you got a bunch of electrons here and a bunch of electrons here.